Today I will be presenting a little bit about what we've been doing with Chill Ice and with our company ICEE.Space, which is also, of course, on our badges. Hopefully becoming an IAF member as well in the near future. So for now, we're talking about Chill Ice, because in 3 years we will return to the moon. And I'm not per se saying we, although of course I hope that some of us will also be amongst those very few special people. But we as humanity will be returning to the moon. And we're not just going there to just go to the moon and come back, but we're actually going to be staying there. We're going to living and surviving on the lunar surface, and later on even beyond. We're going to Mars, we're going deeper into our solar system, and maybe even further, even beyond our solar system as well. However, that is also going to be a very costly and time-consuming revelation. So, I'm not sure. Is it still? Yes. So to practice before we going into the big great out there, we have to practice on Earth. And that's why I founded this company, which is called ICEE.Space. It's, of course, working in space. It's an acronym. So it's also an acronym, isolated, confined, extreme environments in space. And at this point, only here on Earth in space, because of course Earth is also in space, later on also to prepare for actual space missions. So basically what we're doing is we're going to be locking people up in very isolated, confined and or extreme environments. So that's why we started this project, which is called Chill Ice. Again, an acronym, we're still working in space, stands for the construction of a habitat inside the lunar analog lava tube in Iceland. And it's a project that I've been working on since May 2018, so for about 4.5 years now. And we've already had 3 successful missions, 2 successful campaigns, the last one of which actually concluded about 2.5 weeks ago. So we just came back from Iceland as well. And let's see, yes, because we are going from into the Earth to into the universe. But we're not just going to be doing that. We're of course doing that with all of us, with all of humanity. So that makes it not just a space mission, but actually an astronaut mission. And as I said, before we send actual humans into space, which is again very costly, very time consuming, very energy consuming as well, we need to practice on Earth. So that's what we call analog astronaut missions. I think some of you might have been familiar with analog astronaut missions as well. I see some of our astronauts here as well. So I do hope by now that you are familiar with analog astronaut missions. But for those of you who are not so much familiar with analog astronaut, it's basically simulating space. So living life on the moon, as it were, but then on Earth. Partially because we just feel like it's safer, we can implement technologies much quicker, we can make our own rules and we make them up much quicker, implement new technologies. Partially because we simply do not have the money to send all those cool people that are standing right here to the actual moon. So we kind of have to go to Earth. Because life on the moon, it's not easy, as I already said. There are some problems which makes life on the moon suboptimal, I would say, for human survival. First of all, of course, we have the solar radiation. We have micrometeorite impacts. We have thermal variances on the lunar surface. We have the cosmic microwave background radiation. And, well, speaking of the radiation, for example, so on the lunar surface, if you were standing there with your human body, which is about 2 square meters, you will receive approximately 200 times more radiation per day than you would receive here on Earth. Which also means that if you are decaying due to radiation, you will do it about 200 times as fast on the lunar surface. Then the other problem that I mentioned, the micrometeorites. Here on Earth, we sometimes also see them. Actually saw one last night even here in Paris, which was a shooting star. And here on Earth, we just see them burn up in our atmosphere and we make a wish or do some sort of silly human habit kind of thing. Whereas on the moon, these things will eventually kill you. Micrometeorites are teeny tiny particles of dust, usually less than 1,000th of a millimeter in size, and they're traveling at insane speeds, 20, maybe 30 kilometers per second. Which means that right now it would be still in Belgium, it would be coming over towards Paris. Right now it would fly right through me, killing me instantly if I were to stand on the lunar surface, and it would have been gone. It's almost at the central massive already. That's the speed of these kinds of things. You cannot see them coming, you cannot avoid them, you cannot stop them unless with a very thick wall, And if they do hit you, they will kill you. So we need a very thick wall. Having a very thick wall might not be the worst anyway. As I said, we have some thermal variances on the lunar surface as well. So on the lunar equatorial surface, so the equator of the moon, you have a temperature difference between the lunar day and the lunar night of about 360 degrees Kelvin or Celsius. So during the day it can go up to almost 180 degrees above Celsius, above zero, and in the night it can cool down to almost minus 200 degrees. Which means that even if you have an alloy, it will eventually expand and shrink due to heating and the cooling down, and this will eventually cause cracks in the alloy as well, and will just in overall be very suboptimal for your human habitat. And all of these things combined also make for a very cool sort of additional factor which comes in, which is the regolith. So the regolith is a very fine-grained dust that we can find on the lunar surface, and that is because the lunar surface has no surface renewal processes. So all the rocks that are lying around on the lunar surface will have been in that exact location for several billions of years. And all these factors that I just described, the radiation, the thermal variance, the impactors from meteorites, it will eventually weather and break down these rocks until very teeny tiny particles. You can see it a little bit here on Jack Schmidt's face, the only geologist who ever went to the moon. Very cool person. And it's a very strange sort of substance. It has a lot of surface area, it has a very small volume, and it also means that if you breathe it in, it also has a lot of reaction potential. So all the minerals and the metals that are inside this regolith, if you breathe it in, it will almost instantly dissolve into your bloodstream. You will basically giving yourself heavy metal poisoning, which again is suboptimal. So in short, life on the moon, it's not easy. And we need some very, thanks so much. We need some very rigid structures, and we need very thick walls. We need to protect ourselves at all costs. But at the same time, what are those costs? Because going to the lunar surface is a very costly endeavor. Maybe it's a nice question for the audience here. How much do you think that sending 1 kilogram safely to the lunar surface will approximately cost? Well, current estimations from commercial lunar payload services providers, or CLIPS, place that around 1 to 1.8 million US dollars per kilogram. So if we have these nice and thick walls of 2.5 meters thick concrete, we better think twice before we actually send it to there. And speaking of a habitat that is already in space, this is still a relatively small habitat. It's suited to house about 8 people, maybe at maximum 13 people at any given time. And even this relatively small habitat, which isn't even suited for the level of protection that you would require on the lunar surface, it weighs about 420,000 kilograms. So we will need a very, very, very hefty group discount before we can send a small habitat like the International Space Station to the lunar surface. So that's where my job as an earth scientist comes into place. So luckily, we are having a lot more resources available for us when we're at the lunar or the Martian surface than when floating around the relatively emptiness of Earth orbit. And using those local resources, this is called ISRU, or in situ resource utilization. One of the examples, for example, is to have regolith, so the same dangerous stuff that I was talking about. If you were to dissolve it in water and have some cement with it, you can actually make it into concrete blocks. So you can have a lot of help with the protection from, for example, the radiation from these concrete blocks. This was my bachelor thesis project. You can see them, they broke apart here. That's actually good, because if you're testing concrete, of course, you need to know the maximum strength. So you're testing them until they break. But it's actually a very sturdy concrete. Some of them held up to 30 megapascals, which is actually enough to make 2, 3, 4-story buildings here on Earth, let alone, of course, on the moon with lower gravity. We can make much, much bigger houses. Another very cool part of ISRU, for example, is what I call the paradise. So in the lunar north and south pole, which you can see pictured here, there are some vast mineral deposits of water ice. And the reason that we have those over there is because of the rotational axis of the moon. So, of course, the moon also turns around the Earth, and together they turn around the sun. But the moon is almost perpendicular on its axis. So whereas the Earth is about tilted by 23.5 degrees, which causes us to have seasons. So if my microphone would be the sun, and we're tilted a little bit like towards this. Then, of course, in the northern hemisphere, we're closer to the sun, receive more solar radiation, and will be our summer. And half a year later, it will be the exact opposite, and we'll have the winter on the northern hemisphere and summer on the southern hemisphere. On the moon, however, we're almost perpendicular on our axis. So that means that if we have the solar radiation coming in from one side, and we have a crater on the South Pole or on the North Pole, and it's facing down or it's facing up, then there will be no solar radiation ever reaching the insides of these craters, which means that's actually one of the coldest places that we have within our solar system. And average, it's about minus 220 to minus 240 degrees Celsius, which means that everything that gets stuck in there, such as water, will eventually stay there. And over the course of several billions of years, again, no surface renewal processes on the moon, this will accumulate and turn into quite some serious water deposits as well. And the cool thing is actually that on crater rims or mountains located on the North or South Pole, we actually also have the opposite feature. So if you have a mountain sticking out, it will almost always receive solar radiation. These are what we call so-called peaks of eternal light. Some of them have over 90% of the time will receive solar radiation. So that means that we actually have a deposit of water ice, which is a very valuable resource, and almost infinite solar energy coming in together at very small apart places. And we also tested this with Igluna. Actually just came from an Igluna alumni lunch where we went into a glacier in Switzerland, also on top of a glacier. And we did a lot of science experiments here. It's the Matterhorn Glacier in Switzerland. But of course, ISRU sounds maybe a little bit far away. It's actually not that far. Even better, we have already one very clear example of ISRU working on the Martian surface. This is called MOXIE. It's the Mars Oxygen ISRU experiment. And it actually managed to produce just over 5 grams of oxygen within the first 2.5 hours of it being operational. Which is enough for an adult human to breathe for about 2, maybe 2.5 minutes if you keep your pace down. So it's not a lot, but it's a crucial step in technology that we will need before we can actually survive for longer periods of time on the red surface. But I think the coolest place actually to look for ISRU is not just to look for parts of the soils or parts of the rocks, maybe some minerals, parts of the atmosphere. It's actually to look at whole structures that are available on the lunar and the Martian surface, such as lava tubes. So lava tubes are one of the most amazing things that I, as a geologist, can imagine. But maybe not everybody is completely familiar with what a lava tube is exactly. Sometimes it's also called a lava cave or lava tunnel, which are both factually incorrect because a cave is erosional. A tunnel is actually human-made or at least synthetically made. Whereas a lava tube is actually the lava flow itself, flowing down a very specific hill with an exact right composition, with the exact right temperature, and eventually it will start to form a crust on top of this lava flow. And this crust, this will solidify and eventually start to form a whole shield over the flow. And this crust will insulate the warmer inside with the cooler outside, and eventually this flow will continue on, it will dissipate via cracks in the surface, and all that we're left with is this hollow tube, a lava tube. And of course, the final idea is then that we can live inside one of those lava tubes. That's exactly what we did with our Chill Ice mission. So you can see here the habitat in which Mohammed, who's standing right here, our astronaut from last year, actually managed to survive in for about 56 hours. And it's not just that we have those lava tubes here on the Earth. As I said, of course, we have them on Earth, but we also have them on the Moon. And because they are such protected environments, they can actually be this same protective environment for several billions of years. So that means that all the rocks on the inside of these lava tubes will still remain exactly the same as they were when they were deposited several billions of years ago. Another cool fact about the lunar lava tubes is that they tend to be much, much bigger. Because of lower gravity, we can have much larger structures which are still stable. And some of those lava tubes actually are up to 80 kilometers in length and sometimes up to 200 meters deep and 300 meters wide. So that's not just enough for the small eco habitat that you just saw in the picture. It's actually enough to house a whole lunar city. And also on Mars, we have some lava tubes. This is the largest volcano that we have. It's about 3 times the size of France. It's called Altamont. It's close to Olympus Mons, which might be a little bit more familiar because it's the highest volcano that we have. And actually on the western flank of this big volcano, there has been some studies as well to see how much of those lava tubes could actually be there. So these are different types of rheas and lava tubes. As you can see, there are quite a few of them, and this is the scale bar. This is 100 kilometers. So also on the Martian surface, we have a huge opportunity to go into these lava tubes. Again, that was just this one volcano, and there are several types of these kinds of volcanoes. And because they're also on the moon and on Mars and on Earth, and our current roadmap is to probably go via the moon to Mars, it will also allow us to sort of step up our practicing game. So we first start practicing within the Earth lava tubes, then we move on to the lunar lava tubes before we eventually explore the untapped research potential of the Martian lava tubes. Also fun facts, so this is the Jezero crater you can see over there, which is where Perseverance has landed and where Ingenuity is flying. And here in northeast Syrtis there have also been some lava tubes found. So we're basically about 80-90 kilometers away from actually going into one of those Martian lava tubes, which of course is still quite a long distance to walk in one day. But at the same time, if you see that Mars is almost 200 million kilometers far away right now, it's actually very, very close by. But then, of course, there's the problem of the accessibility. So as I mentioned already, we haven't been inside one of those lava tubes before. We don't know what they look like from the inside exactly. This is what we are, of course, wanting to research, but it also answers a crucial, or gives us a crucial problem. How do we know that we can get in? How can we make sure that we are safe by going into these lava tubes? And especially also, is it possible to find out the size of a lava tube remotely without having to send humans into a dark and unknown abyss, not sure in knowing if they are ever coming back alive? There are some moral dilemmas with that. So we need to know what they look like exactly. So this is also a study that I did in preparation for GeoICE at the ICEE.Space in Hawaii, where I used magnetometry to find out whether there would be a lava tube in the subsurface. So with magnetometry, you're basically looking at the presence of the Earth's magnetic field. You might be familiar with it from a metal detector, where you're sort of beeping over the ground. And eventually, when there's a material that is more magnetically conductive, it will cause a small anomaly, and you will be able to read it as a positive sort of beep or ping. And then the cool thing is that the rocks that we have on the lunar surface, or at least in the EuroMoonMars, but also on Hawaii and on Iceland, they are very enriched in these kinds of magnetically conductive materials. So there's sort of a constant positive anomaly when you're flying over the surface. And the only way to have a negative anomaly is to have no minerals, and therefore no rocks, and therefore a lava tube. At least that was the theory. To have a positive anomaly everywhere basically, and only a negative anomaly when we're flying over a lava tube. So we tried it out. I didn't have a drone, so I used astronauts as tethers as well. And eventually, I'm not sure if you can see it on the screen as well, but there's a very clear line here which actually moves over a lava tube, and you can very clearly see a big dent of almost 14% in signal strength when flying over a lava tube. So this might be enough, not just here on Earth, where we of course have a very strong magnetic field, but even on the lunar and Martian surface, where we have latent magnetic fields from the lava flow themselves, to see a small deviation of several percent. And as I said, it's not just about going there, it's not just about giving ourselves the challenge of actually going into space and living on or under the lunar surface. It's also about understanding our own planet better. On Earth, we don't have any really old rocks. Almost all of the rocks will either have been subducted already, they have been reworked, there have been new volcanoes, there's weathering. Whereas on the lunar Martian surface, they can be much, much older. And especially if you have a place on the surface which is several billions of years old, where there's no radiation, no meteorites, and no other types of weathering. So inside these lava tubes, we will find the key to understanding the history of our own planet and the history of our solar system much better. And with that, eventually, we actually started the whole GeoICE project. So in 2018, we started out as a sort of a scouting campaign to see whether it would be possible to do any kinds of analogues in Iceland. And eventually, we basically just hosted a mission last year and this year as well, where we had a longer mission. So we were located this year in a cave which is called Surtsetlir, which is about here in Iceland. You can also see Reykjavik, the capital of Iceland, over there. And we locked our astronauts up, of course, in a space habitat. So our space habitat was actually designed by students and faculty members of the Wilson School of Design of the Quantum Polytechnic University in Canada. And they built this whole habitat for us to be deployed inside a cave. And of course, astronauts are no real astronauts if they're not also wearing astronaut suits. So we had, this year we also had Borb suits and Astroland suits. Astroland's a company in Spain and Borb's a company from the US, where we had new helmets from to help a little bit more with the fogging. Unfortunately, because of the high humidity inside the Earth lava tubes, we still had some fogging inside the spacesuits. Let's see. And it's also, of course, a very nice challenge of not just doing pure engineering and pure science, but we are very open to all kinds of interesting projects for space. Everybody who has a passion for space, has an interest in space, can join us with the Chill Ice missions. So over here you can see the Lunar Zebra rover, which I think also shows a little bit how close we are by looking back to Earth. It's not just going further into space, it's not just going further into the universe, it's also looking back and reflecting on ourselves on Earth. And I don't think we can do that much better than with art. And I think this video, which is taken last year's campaign in 2021, actually shows you a little bit of what I mean with nature's art. So over here you can see lava droplets coming from the ceiling. They look a little bit like stalactites, but they are actually not proper stalactites, because these are actually parts of the lava flow when it was still flowing freely through the lava tube, sloshing up to the ceiling, dripping down, and then condensing whilst dripping down. These are also highly protected in Iceland, so you're not allowed, of course, to break them or take them with you. But I think if we can already imagine these kinds of alien structures, something that is... I have never seen anything like this anywhere outside of a lava tube. And then to imagine that, again, on the lunar surface, these types of features, these types of structures can be so much bigger because of the lower gravity. I think it's just going to be very, very exciting to see what the humans will experience as soon as they actually make it into one of those lunar and Martian lava tubes. So, looking forward, these were the astronauts from the first mission last year. It's going to be sort of the ultimate challenge. And why do we want this challenge? It's the breaking through of our comfort zone. So right now our comfort zone is, of course, here on Earth. We have a few humans living up in orbit around Earth, but we don't really have humans out in space. And it's only when we give ourselves these kinds of challenges, where we push ourselves further and further and further, that's when we actually will find the problems that we can solve, not just to solve human life on Mars or on the Moon or beyond our solar system, but also to solve the problems of human life here on Earth. This is what we call serendipity. Finding that what you needed, but you didn't even know that you were looking for. And it's something that we see as a very strong theme throughout the space sector in the several decades that we already have within the international space sector. Whether that's from technology, like this camera that wouldn't work without space technology, a phone that would not be able to communicate, the battery powers in my laptop over there, which would not be able to work, and of course solar panels. We've had this technology for solar panels for almost 200 years now. The first solar photovoltaic cells came from 1830s, but we never really had to invest in them until there were some crazy guys who said, like, we want to go to Jupiter. And then you need stronger solar panels. You need a radiothermal generator. And it's those kinds of things that will allow us to move beyond our planet, but also to make the life on our planet better. And it also has to do with the vulnerability. As you know, humanity is already changing the Earth system drastically at this point. And it's only going to get worse. We will have more humans and we'll have a higher quality of life overall, which also means more pollution, more energy, more resources that we will require. And it's only that you basically go beyond the Earth, where you have to pay $1 million US for just 1 liter of water, that it will actually start to make sense to completely reuse all of the water that you're taking with you to the moon, not to throw it out into the open vastness of space, but actually recycle and reuse it and repurpose it as well. Let's see if it's going to the next slide. Here's some very nice but very big pictures as well. And it's not just a vulnerability in terms of the planet, but it's also vulnerability in terms of us as the human race, because we are only limited to one planet at this point in time. And it's basically all species that we know of have the need and the drive to survive, to procreate and to thrive as well. And as long as we are living on one planet, there is the chance of a human extinction. And it's simply that we are the first species, at least that we know of, on planet Earth that has the capacity to go beyond planet Earth to avoid like a mass extinction, like the meteorite that struck the Earth about 66 million years ago, which killed off all of the animals on the land, which were over 25 kilograms. And it's basically just this need for survival that will allow us to go beyond the Earth and to go into space. And that is also the impact that I try to have with my company ICEE.Space. It's not just to make a better and easier and safer life in space, but also to have a better and safer life on Earth. And it's this part of the inspiration that I think we can all use from space also to make our lives on Earth a little bit better. And that's the end game. That's the goal. And yeah, it's also our slogan, from into the Earth to into the universe. And thank you very much.